Thank you very much for the introduction. Much of what I'm going to present here today is joint work with some people I met at the Algorithmic Institute. Matt Kusner, Chris Russell, and Joshua Loftus. So what I want to talk about here today is mix between having some sort of introduction to this whole idea of what we call structural causal models in artificial intelligence as seen from the point of view of machine learning. And in particular, motivate that from one specific application, which in this talk is going to be algorithmic fairness. So if you don't know much about it, don't worry, I'm going to present some examples, but the idea is in which sense the idea of causal model is required or in one very broad direction, kind of essential to provide satisfactory answers to problems such as algorithmic fairness. So without further ado, let me give you a starting example. So I'm going to refer to that throughout the talk. You have a typical prediction problem that is going to be used in a life-changing decision-making scenario, which is admissions to college. So you have to somehow try to make offers to students. You want to be able to say, this student is going to be doing well in my program, but I need to somehow predict that from current features of the candidate. So you may have, for example, past exam indications of the student. If it is in the US, you can have something like the GPA that measures how they did well during high school. You can have LSAT, which is a specific standardized exam. And with that, you can try to predict some particular measure of success in undergraduate school, which in this case would be first year average. So you have the data for that you can use to build your typical statistical model, your typical machine learning algorithm, to try to predict this first year average and make offers to candidates accordingly. Now, there will be some issues there on whether the whole decision-making pipeline is not biased against particular demographic groups. You don't want, for example, to show that your admissions process in some way make life more difficult to people from particular racial backgrounds or gender or particular areas where they live and so on and so forth. So you kind of like to understand that some attributes are in one sense protected. You don't want to discriminate people according to some particular dimensions such as race and gender. And even though we have some set of features which are okay to use, they somehow are going to get intertwined with the so-called protected attributes when you try to make your prediction. So in the examples that I'm going to describe here, you have X as the set of features of the individual that are easy to or okay to use for your prediction. You have the set A of protected attributes that in one particular technical sense you should not discriminate against. And then you have the outcome of interest, what I'm going to call Y, which is the one that you want to predict during your decision-making process. So as I said, Y is going to be the first year average of the student in this particular example. And whatever prediction you make, I'm denoting this slightly different with this Y hat notation, because it's going to be important to contrast what your prediction is against what the actual real outcome was. So Y hat is the prediction, Y is the actual outcome in the real world. So we have all this sense that if you don't want to show discrimination, then one way or another, some independence of some sort between what these protected attributes say and what your prediction stipulates. So in one sense, you have this feeling that Y hat and A, one way or another, should have some degree of independence. You don't want your predictions to be racially biased in one way. I might suggest to you, you should not have some sort of statistical association. And people play with these different variations of independence where they want to assert that a particular outcome of predictive algorithm is unbiased. And some of these variations can be denoted in a more formal way. So these are here just some examples of it. This so-called demographic parity that you see there in the first line just means my prediction in the protected attributes just are completely independent. They have nothing to do with each other. The second criteria is in the middle line, sometimes called technically equalized odds. It tells you if you actually knew the true outcome, then my prediction and my protected attribute to be independent. The third one that see this, they are sometimes called calibration. If I told you my prediction, then my protected attribute and the real world outcome will be independent. So the last one, for instance, is stipulating that your Y hat is a very good predictor of Y. Because if you knew Y hat There will be no information left on Y to tell you about any other attribute. So these are some examples of criteria that people came up with. They all rely on this notion of statistical association. And it turns out, and we can show this technically, that they are self-contradictory. You cannot satisfy all three of them at the same time, because this would imply something very trivial about the cases in which you can guarantee that. So one simplification of what this means is, in many cases, to be able to satisfy this, essentially your prediction Y hat has to be the tossing of a coin. Basically don't have any way of making informed predictions if you try to satisfy all three of them at the same time. Now, what bothers some people about this is precisely this: don't kind of grasp exactly what would be a good operational way of satisfying our intuitive notions of fairness. And when you try to just boil everything down to associations, there are all sorts of counterintuitive ways of constructing something that satisfies this criteria, but still don't feel right. So one example of what you can do that tricks maybe your regulators or somebody who wanted to convince that you're doing the right thing is to just downweight and upweight particular ways of combining subpopulations so that you can get these particular properties. So the example I have here, it might be a bit convoluted, is if you have a particular minority, so imagine here A, for example, as being race and A prime being a particular racial minority that is highly associated with a particular event. So in this case here is whether these people take particularly remedial classes when preparing to apply for law school. And so you can build a predictive model so that you use this as a surrogate to say, yes, I accept you, knowing adversarially this is actually, sorry, I should say, if you have this high common event among this group, then you say, no, I don't accept you, so I'm going to hurt the majority of people there because the majority of them do take these remedial evening classes, but you can try to balance it back by saying that if you don't take that, then you're basically guaranteed to enter. So you can play the weighting of these two criteria so that it looks like you're being biased among different racial categories, but in fact the people that you accept from this minority are actually very unlikely people who don't come from a particular walk of life, so to speak, as common knowledge will tell you. So these associations can be tricked. You can just basically weight them down in particular ways that these look to be satisfied, but they don't correspond to our intuitive notions of fairness. Now, all this motivational background that I gave here to you is to kind of introduce ways of trying to make explicitly how your data is generated. Because your data by itself does not tell a so-called causal history behind it. So what a causal diagram tries to tell to you is some sort of sequence of events that are causing each other that would would explain the associations that you see in the end. I'm going to get a tiny bit more formal later. Right now, don't worry about what the formal meaning of this diagram means, but intuitively, these arrows represent the direction of causation. So for example, this means A causes Y, but not vice versa. And you can put in the diagram not only the outcomes that you see in the real world, but also the outcomes coming of a decision-making process. So both Y and Y hat would appear here. So here A could be race and X could be, for like the feature that I mentioned before, taking remedial evening classes or not. Y is actual first year average. Y hat is a prediction of first year average in this school admissions problem. So what this does tell me is how the associations emerge. And when I'm going to talk about causal inference later on, I'm going to talk about how different interventions on this process will generate different outcomes. So how, given this story that you see here, if I try to modify something by an action or by intervention, parts of it will change. Now, one way of understanding why associations can be hard to pinpoint without further knowledge is that different causal diagrams would somehow amount to the same associations. They would tell a different story on how the data was generated, but you could not tell them apart from the associations you observe. So you can have, for example, ways of disentangling the sources of variation of a particular random variable so that you can design particular interventions or particular ways of extracting from the data the unwanted components of that variability. So I'm going to get to this later on, but if you imagine that the outcome itself might be unfair because of different choices that people make during their history, you may try not to think of the true outcome as being unbiased itself. So not only your prediction y-hat can be biased according to some intuitive criteria, but even the real data might be biased. And then you're kind of in a conundrum there. What should I do? If I want my predictions to be unbiased, even getting a perfect prediction would be a problem because the real world process might be unfair by itself. So how can I possibly solve this problem when I have unfairness in the data generating process itself? Now, all of this can be like a convoluted mess, and hopefully what I'm going to explain for the rest of this talk is how to pick them apart and making it a bit less challenging. It's still going to be a challenging problem by the end of the day, but hopefully it does provide you some clarity on how to even begin to tackle problems of algorithmic fairness. Now, as I mentioned to you, some of the most intuitive basis behind fairness is try to avoid having decisions based on something that is associated with a predictive attribute. So some of the earlier attempts on solving algorithmic fairness would start from what you see in this diagram from a non-causal perspective. So you have your outcome y, you have your protected attribute a, and you conjecture some latent variable, some variable that you do not observe, which I'm going to call z here, that explains the variability of y that is not explained by your other variables. So a, x, and z together explain the variability of the outcome. A is something that really you don't want to be influenced by. So one idea there is try to remove from y any sort of variability that is independent of a. So you can put together a model where this variable z there will try to accommodate whatever is the variability of y that is remaining after you account for the protective attributes. And once you extract the z fellow you see there, then that's fair to be used in any predictive method that you want. So you could plug that in whatever machine learning method you want, whatever statistical method you wanted, to build a predictive y-hat that tries to reconstruct y. Now the problem with that, and you can show that mathematically, I'm not going to walk through this slide, but I left this for your reference, is that this is a U-pose problem. There are many ways of doing this decomposition. So there are many ways of building this z variable there that is independent of a. And again, going back to square one in one sense, that you don't know how to justify one from the other. You need some sort of domain knowledge to be able to make a more formal claim that you're trying to do the right thing according to intuitive notions of fairness. And one way I'm going to do that is to appeal to something called the Structural Causal Model, which is an idea that has appeared in different guises on different literatures. So you can see this coming earlier on from the genetics literature, from the social science literature, building up on statistical methodology across the 20th century. And from us who are coming from a more machine learning or AI point of view, were very neatly put together by the work mostly of people like Yuda Pearl from UCLA, which you can read more about in some more of his high-level books explain this idea. So there are some references which I recommend as introductions to this framework. Now, much of the idea here is you break apart variability in terms of modules where you can do some particular hypothetical intervention. So our intervention here is what tells apart a model that is causal from non-causal. You'll be able to, we want to understand what happens when you modify a system, override it somehow, how the consequences of that action propagate through the variables that you measure. So this is going to be represented mostly in terms of graphs, and I'm going to explain this mostly in terms of examples. But this is the key assumption that you're going to make here, that you're able to say something about what changes and what doesn't change when I intervene in the world. And to be able to tell apart things that change and don't change, or things observed from things that you intervene, that some new notation needs to be added here. So following this particular point of view on causal models from Pearl, I'm going to adopt his notation, and much what he does is in terms of this thing called the operator, which I'm going to explain next. Okay? It's a way of representing how you get into a new regime, how you get into a new data generative process the moment you intervene on a system. So this is a prototypical example. This is probably one of the most famous success stories of epidemiology, showing the link between smoking and lung cancer. So this is pretty much taken as a fact that smoking is a major risk factor for developing lung cancer. There are, of course, many subtleties there, meaning about the dosage, how much smoking it means, that the way where to get exposed, directly or indirectly. Let's just simplify that. Say there is a well-defined way of measuring smoking, a well-defined way of measuring lung cancer. All I want to establish here is the difference between causation and association. Because you know there are different concepts. So how do you represent them differently if the language of probability itself doesn't tell them apart? So what you see on the left-hand side here is a system where I'm postulating explicitly that smoking is a cause of lung cancer, but you also have possible common causes of it. We call the confounders of a causal relationship. So when you're not thinking about causation in your usual predictive modeling setup, you may be interested in quantities like this. The probability of developing lung cancer given that you're a smoker. There's a prototypical probability question you might have. And you can use whatever typical observational data that you have, in whatever model that you have from probabilistic modeling, to answer a question like this. But this is not the same thing of trying to know the link between lung cancer and smoking, because you have these confounding factors here, which might actually explain away even the complete association between the two. It could be the case that this link didn't exist, and still the association between these two guys would be strong. So this could be strongly associated, but represent no causal effect. How do I formalize the difference between what I want to understand of a cause effect from what I want to understand from an observation association? Well, the idea is precisely that the notion of a local intervention leaves parts of the system invariant and modify other parts of the system. So my operationalization or intervention here is what you see on the right-hand side diagram. Here is the representation that I'm forcing somebody to smoke or not to smoke. I'm controlling that variable. It's not a random variable anymore. It's a control variable that I'm setting by design. So the rectangle that you see there actually means that this is not a random variable anymore. I'm controlling that. And because I'm controlling that, any other input to it gets erased. I override any other source of variability for that. When you have that, it's a different regime, right? It's a different data generating process, but you have to have some link to the observational regime that you have here, which is uncontrolled. Otherwise, I cannot learn anything from that to answer what happens in this system. So the key assumptions are assumptions of invariance. That, for example, you're only modifying this module, while the others remain the same as in the original system. So whatever data generating process for the common causes are, they remain the same. This outcome model here remains the same, but this is changed. I'm still interested in a conditional distribution, but not under the original random variable interpretation of smoking, but under the control signal of smoking at a particular level. And this do operator does only denotes this, that this is now controlled by somebody. So the system disconnects these two guys while keeping the rest of it invariant. So if I know about the distributions here, I can carry them over there to calculate this quantity. And this would be how would you summarize a cause effect of a small lung cancer from data that is uncontrolled. So a randomized controlled trial might give you a system like this, but in something like the link between smoking lung cancer, you don't have a randomized controlled trial because it's completely unethical to do this to somebody, right? You're not going to force somebody to smoke or not. So this is the key idea there. I'm already using a lot of time here. But this key idea by itself only answers what you can do in terms of predicting the effects of actions. For a notion like fairness, I may need to get a bit deeper on here and get into modifications to things that already happened. The reason for that is when you think about discrimination, you might think in terms of the so-called counterfactual queries that you see there. So if you ask yourself, this job application process, was there any sort of racial discrimination behind it? You may want to formulate this in a counterfactual way by saying, oh well, this applicant came from a majority group. Other things being equal, he was actually being given that job, which he wasn't given. So contrary to the fact, we imagine a hypothetical world where things have been switched. You keep everything as it was, and then you see what the implication of that was. This is called a counterfactual formulation. You can play this in many different scenarios. So low application process, same thing. This candidate didn't get it. Well, was there discrimination on that? Let's ask this counterfactual. Imagine this person has a different background. Would the outcome be the same or not? If it wasn't, there's some intuitive sense there that discrimination was at play. Now, of course, this is just wordplay in one sense. If you want to translate that into a quantitative background to answer this with data, you need to be a bit more formal of what these counterfactual queries mean. So if you think about this notation that I just introduced to you, you may have your background A, as you observed, some other covariates. Then imagine a cause effect by manipulating this protected attribute, changing it to a particularly different value from what you observed. Now this looks very weird because now you have the protected attribute showing up twice, once as a random variable, what we really observed, and once as a counterfactual intervention, changing this to some value that you know wasn't the case. And this doesn't go together. This doesn't make much sense semantically. It's not in the original formulation of what intervention means in terms of causal graphs. So you need to extend this formulation beyond effects of interventions, introduce explicitly what a counterfactual means. The notation I'm going to use here is a standard notation in statistics. You imagine a new set of variables on top of the variables that you observe in the real world, which are counterfactual. They represent results of events on parallel realities, parallel worlds where a particular intervention took place. So now when I say, for example, y parenthesis a, it means my outcome, like first year average, in a world where I actually changed, I forced a to take the value little a. This is a different variable from the factual observed variable first year average. It exists only as a thought experiment. If you try to make sense of it, maybe let me just show this with a diagram. You can start again from your causal diagrams and come to grip that you need to introduce new variables beyond the variables you have, because counterfactuals don't belong to the same reality, to the same observed world as the one that takes place. They're contrary to the fact, right? They cannot be the same variables you started with. So the way I structure causal model deal with that is they imagine the world is this sort of pseudo-probabilistic world that your random variables that observe are effectively deterministic functions of what you see and whatever remains to be seen in the world, are the hidden variables that explain the variability. So if you augmented the diagram that I started with there, you can imagine each variable here as an extended latent parent, so to speak, pointing to it, with the remaining factors that causes it. And this is given by a set of equations that you're going to call structural equations, how these relationships take place. So when you have a counterfactual word, you have new variables. So this is what you do. You literally add more variables to your system. In this counterfactual word, your protected attribute has been intervened, has been controlled externally. So this is here is not a random variable. This is actually a decision variable that has been controlled. But only things that are affected to it will take a new counterfactual value. So these background variables which are hidden, they remain as they were. They're not being affected by your intervention. But things that follow A on the diagram, they will have counterfactual instantiations. So this just naturally reflects a kind of twin network from the one that you started with, where some of the parental relationships are carried over. So if this outcome Y here has this hidden parent, well, this hidden parent will also be explain the variability of the counterfactual version of Y, the counterfactual version of first year average. Why I explain this in the context of fairness? Because this allows us to formulate more formally what counterfactual query means. So let me go here. So when I say had protected attributes been different, other things being equal, the prediction would have remained the same. So my desiderata for something which should be fair. I can translate that English sentence into a statement that uses this formal language of counterfactuals. I can say these two variables, the factual outcome and the counterfactual prediction made, are equal in probability given the evidence I've seen. So the evidence you've seen, which are the covariates and the protected attribute, remain the same. They don't change. It's what happened, it happened. What might change is your counterfactual prediction had the protected attribute take a different value. Okay, so it boils down to a criteria of what we call counterfactual fairness. It boils down to satisfying this particular equality between the prediction that you're making and the alternative counterfactual prediction. So if you satisfy that according to this criteria, you satisfy this notion of counterfactual fairness, that would be an operationalization of fairness. Now everything that you see here can be, well, how much time do I have left? Because in basically 10 minutes or more? 15?
Yeah.
So everything I've mentioned here can probably be better understood as an example. So this is a starting example, which is a toy example of what would happen in a car insurance company. So you want to price a car insurance policy to a client. You have some knowledge of this client's history, and your decision might hinge on the probability of that person suffering a car accident in the next year. So this is a completely toy example that formulates or postulates how you think a causal model or the attributes you see would come about to produce a car accident, probabilistically speaking. So in this diagram we have protected attribute. Here is just a placeholder for any sort of demographic information you want to use. Here is a potential observable feature that this person owns a red car or not. Here are hidden variables, all sorts of other causes of this event of owning a red car, and possibly common causes of this person suffering an accident within a year. See, there is no causal link between the demographic attribute and suffering an accident, which is encoded by a lack of an edge between these two vertices in this graph. Now, we should try to make a predictive model. The outcome variable is accident. This is what you want to predict. And the remaining variables can be used potentially as inputs to any predictive model you want. Logistic regression, for example. Now, if you just try to use this on-red car variable as your input, thinking, well, this will be enough to be fair because I'm not using the demographic attribute directly. I'm just using this person owns a red car. I'm not explicitly using in any way here the demographic factors of this individual. So I may trick myself in thinking I'm being fair because of that. And now the thing, of course, is you ask yourself whether this is counterfactually fair or not, in the sense that I formulated here. Well, what you should do is imagine would this prediction change if I imagine I actually belong to a different demographic group? Now, as before, I'm going to create a Twain network. I'm going to replicate some of these variables, creating counterfactual versions of them. So my protect attribute is A. Imagine a change on it. So this becomes now a control variable set at a different value, the value A prime. There will be a counterfactual version of owning red car. So here I'm indexing that using this notation, my own red car under A prime. This variable, a quantum original formulation, is caused by A, so this will change under my hypothetical counterfactual word. And by the same reasoning, my prediction y hat that I had here will also incorporate the propagation of this change. So this guy here in the factual word and this guy here in the counterfactual word, they are not going to have the same value and probability if I change this guy. So even though I didn't use A directly as input to y hat, it will change under intervention of A. So this cannot, the definition that I have here cannot be counterfactually fair. Unlike this different predictor that I'm building here, which feeds from this common cause unobserved, which is not affected by A. So under a change of A, this predictor changes, but this one doesn't. So this predictor would be counterfactually fair, but this would not. All right? So in practice, we'll need to somehow learn something about these latent variables to be able to be the predictor for this guy. Let me skip this. So what does this mean in terms of creating a practical algorithm? Well, essentially, you can build whatever, you can use whatever method you want off the shelf to build a predictive model, but the difficulty here is on using the right variables, so to speak. So variables which are not affected by A being the protected attribute. So in the radical example, it boils down only to that hidden variable that explain the other non-discriminatory sources of variability of owning a red car. So we need to infer that from data. One way of doing this is building a full-fledged probabilistic model, turn the crank of whatever probabilistic inference method you want, that given the things that you do see, you are able to reconstruct information about you. And just plug that in a predictive model in order to generate your prediction y hat. So in other words, you can think about the evidence that you did see in the factual world. This is fair game to use, because this counterfactual fairness measure here does use what happened in the real world, but only as means to infer something about variables which are not caused by A, which then you can plug in whatever method you want, like logistic regression optimization here, to build a model in which you create your prediction at the end of the day. Okay, so this is the main idea here. It looks simple if you think about just as a method for feature extraction, but all the pipeline to create this feature extraction machinery is conditioned on a postulated causal model, which of course I'm not claiming in any way is easy to get, to obtain from a easy day's job. So to give you an idea of the challenges behind it, this is a final example where it's still toyish, but it shows to you the challenges on put this to work in practice. So this is a loan, supposedly loan approval system. Again, let's just imagine you have one covariate that is not protected, is whether this process is currently employed or not. You could think about this being a fair variable to use in a predictive model, but again, it will depend on the assumptions and judgment values. So if you think of this as your postulated causal structure of the world, where being employed or not is a result not only of your qualifications, but also whether you live in a society that is prejudiced against you and might hurt your chances of getting a job. Based on that, if you think this model is correct, and you think that it's unfair to do anything that is not counterfactually unbiased, then actually using this variable would not be a fair game, because if you change this guy, it propagates to that and to propagate the prediction. So under this whole cascade of assumptions you're making, you should not be used current employment situation in order to predict whether this person is be able to repay a loan or not. It's not that this information is not useful to predict it, it definitely is useful to predict it, but you're conflating different signals there, some of which are not under control of the individual applying for the loan. And again, this is a judgment call. This is agnostic to whether you should label this as unfair or not. But if you follow the counterfactual fairness definition, this will not be fair because it includes a component that is directly affected by your demographic attribute. So ideally, you try to infer this variable and that variable and just use qualifications as part of a low and predictive model. But it may be a tall order to infer latent variables like this with very little information that is actually observed. You may try to complement or try to look for more data that allows you to better infer these latent variables. It doesn't mean it's going to be an easy test even under this situation, because there might be all the sorts of unclear causal directions to be postulated there. Okay, so I don't want to give you the impression this is something that's very easy to use, because even though the final algorithm can be very simple, all the set of assumptions that need to build can be very complex. Okay, so you can of course refine this notion to be more specific to particular pathways, so to speak, in your graph. This is a famous example on whether Berkeley was gender biased in the 1970s in the admissions process. It was definitely a very strong association, negative correlation between being female and being accepted in Berkeley. So they actually been taken to court on that. And when there was a statistical analysis behind it, they broke apart in the choice of degree that applicants were doing. And by choice of degree, the association was actually inverted. So actually, being female increased your chances of being accepted in Berkeley, conditioned on the major you apply to. Okay, so if you think about the notion of counterfactual fairness here, you may judge, again, this is a judgment call. This is not given by any algorithm. This is a judgment call that is okay to discriminate in terms of choice of degrees, because some degrees are going to be harder anyway. And you can express the notions that I mentioned to you before in terms of more path-specific cause effects, which I'm not going to get into detail here, where you define counterfactual fairness only on the effect that is propagated by this red arrow. Right? So this is the bottom line. The easiest part is actually by the end of the day turning the crank of whatever predictive method you want. The difficult part is postulating causal assumptions, which will allow you to extract variables which are not within these unfair paths that you come up with by judgment calls. Okay, so I have a simple case study here, which is mostly synthetic, which I hope that'll take 2 minutes.
Yeah.
Again, the data is real, but of course I'm not claiming I'm an expert on the social research that is necessary to create a causal process out of it. but the data is from actual law admission school in the US. As I mentioned at the beginning, first year average is your goal to be predicted here. So these are toy models, again, just for illustration purposes. 2 ways you can define a causal process. So race and sex are the protected attributes. GPA, as I mentioned to you, is somebody how well did in school. LSAT is a standardized exam. And first year average is the one that you're really interested in predicting here. So you can postulate some latent construct on the knowledge that this person has. That is a common cause of these 3 outcomes you see there, independent of the demographic factors. Maybe it's not. I'm just saying under this model what's going to happen. I may have different latent structures. This is a variation of the model where you have this individual latent values per outcome, which are correlated themselves. These models are observational equivalent. They actually explain the same observations, but they have different causal meaning. So this is another thing, which is another can of worms I can explain another day. That the choice of latent structure matter too, and not necessarily be able to tell them apart using data. So again, it's a matter of knowledge behind the domain that tell you which latent structure is more relevant in this case. So we can write down a model using the standard tools of probabilistic inference, like Gaussian distributions for GPA given these 2 factors with 3 parameters. You can fit this model to data. First year average here is normal. LSAT, I don't remember why, but it's drawn from a Poisson distribution. And this latent variable can set its scale and variance arbitrarily. So you set this on normal 0, 1. You postulate this model, give data for each individual. You can infer what this variable is. Once you infer this variable, that you plug in this case, into a linear regression model, instead of plugging in GPA and LSAT. So you lose some information here, using this variable instead of these 2, which are indirect measures of that. Okay, so with that, you can do some sort of assessment on how well you do using the full data, because with more information you should do better. But this wouldn't be fair. And by restricting the values to only those which are fair under the model assumptions, you can show that you lose a little bit in predictive ability, but you do retain the properties of fairness that we drew as desirable under our framework. So one slide of conclusions. Causal inference models for postulating how the world works, judgment calls to see what's important in standard machine learning predictive methods. You combine these 3 for that. There are also other things to take into consideration here, including how to make assumptions more robust. And one of the most important things that people are trying to work now is how do this unfold in time? If we have a feedback loop in time, how this will be represented within this framework. There's still some work in progress to be done on that. Okay? Thank you very much.